Hey Team Bio, sorry I'm recording this screencast so late for you, but here it is. Also, I'm in the SAC doing SAC duty, so if there is background noise such as ping pong or video games, that's what it is, SAC duty. Okay, today's screencast is on chloroplast structure, photosystems, and pigments. So let's first start out with the structure of a chloroplast. I'm going to do this in green. So here. Okay, a chloroplast is an organelle found in plants and as well as some protists, and it's actually a triple bilayer. So here, if this is the chloroplast right here, it's embedded within the cytoplasm, which will be all around it, and there's first an outer bilayer and then a middle bilayer, and there's actually a third lipid bilayer inside the chloroplast. It has a funky structure. I'm going to draw it all out for you and then restart the screencast. Okay, so here it is, the fully finished chloroplast. So you'll notice that there are these funny little, almost jelly bean looking stacks of discs. And this is all actually an interconnected membrane. It's contiguous, so one stack of little jelly beans is connected to all the other little stacks of jelly beans. And a stack of jelly beans is called a grana, G-R-A-N-A, and a singular little jelly bean right here is called a thylakoid. Okay, so grana and thylakoid, and inside a thylakoid, or inside a stack of thylakoids, the grana, is or I guess the whole system is called the TMS, or the thylakoid membrane system. I'm just going to abbreviate it here as TMS. And remember, these are all connected. And then outside of the TMS, but still within the chloroplast, kind of like the cytoplasm of the chloroplast, is called the stroma. Not to be confused with stomata, the structure through which gas exchange takes place in a leaf. So this is where photosynthesis is going to take place. And I'm actually going to zoom in on one stack of thylakoids down below here. And we're going to use that to talk about basically how photosynthesis is taking place on the TMS. So if here is one thylakoid and here is another right here. Inside here would be the TMS, the thylakoid membrane system, and outside we'd have the stroma out here. So this is one thylakoid. And embedded within the membrane of the thylakoid are going to be all the pieces, the enzymatic pieces that are going to be responsible for the process of photosynthesis. So you are all familiar with some of these things, and the first one I'm going to draw here is PS photosystem 2. And following photosystem 2, there is an electron transport chain, or electron transport system. I'm going to call it an ETS, electron transport system. And then additionally, there is photosystem 1, and photosystem 1 is followed by another ETS, electron transport system. You might wonder why photosystem 1 comes after photosystem 2. It was actually discovered first, and it's the more, it evolved earlier in life's history. So that's the reason we call, even though photosystem 2 comes first in the process, they have funny names. Anyway, okay, so the purpose of the photosystems is to gather light energy and use it to excite an electron. They then pass on that high energy electron to the ETS, where it's taken like say you were rolling a bowling ball off a cliff. Okay, someone just came in and asked for ping pong balls, and I completely forget what I was talking about. I think I was talking about rolling a bowling ball off a cliff. So, like if you roll a bowling ball off a cliff, you can't really capture any of that energy that the bowling ball has when it hits the ground. But instead, if you were to step it down some stairs, actually, this is not a good analogy at all. I'm going to use instead the analogy of a car. So you fill your car with gasoline, and you could just light that gasoline on fire, and your car would explode. But that wouldn't be a very useful way to use the energy contained within the gasoline. It's much better to take small pieces of it and slowly combust it, and then use that energy to convert it to useful mechanical energy and push the car forward. So, just like that example, a photosystem excites an electron, so it's like a tank of gas, and then the ETS slowly combusts that energy, so to speak, and uses it to do useful cellular work. And I'm going to leave describing what the ETS actually does until a later screencast. But you should know that it slowly steps down an electron in energy to do useful cellular work. And the rest of today's screencast is going to be talking about the structure of the photosystem and how it actually excites electrons and gets them to be able to do useful cellular work. Okay, so a photosystem is composed of many different molecules of chlorophyll. And chlorophyll is, for the most part, an organic molecule, meaning it's made up of carbon, but it also has an inorganic part. So if this is a molecule of chlorophyll, it kind of looks like a lollipop. The green part is the organic part, and this red dot in the middle is inorganic. It's actually a metal ion, or a metal atom that becomes an ion. So metals are very good at both gaining and losing electrons. As you all remember from chemistry, I'm sure, they're good at being both oxidized and reduced. When you lose an electron, that's oxidation. When you gain an electron, that's reduction. In this case, in the case of chlorophyll, this metal ion is really good at being oxidized, meaning it can easily give up an electron. So how does it give up that electron? Well, if we were to look at the atomic model of what this metal ion looks like, I guess I should draw it in red. Okay, so now we're going to zoom in on this metal ion, and here's the nucleus right here, and surrounding the nucleus are electrons, and electrons form, they occupy different orbitals around the nucleus, and it's not really like a planet orbiting the sun, but for the sake of simplicity, we'll depict it that way here. So electrons occupy orbitals, and they can actually be bumped up from one orbital to another orbital, a higher energy orbital, if they are hit by a photon of light. They'll absorb that photon and then bump up a new energy level. So if we have light coming in and striking this electron, it will bump up an energy level, and then conversely, this electron can fall back down to its original energy level, and it will emit the same photon of light, or the same frequency photon of light. Okay, so electrons have this property which they can bump up and down in energy levels by either absorbing or emitting photons. So photosynthetic systems take advantage of these properties of electrons, and here's what they do. So if we have this chlorophyll molecule here, I'm just going to schematicize it as a single dot. So within a photosystem, a bunch of chlorophyll molecules will all be lined up in a row like so, and they'll take on this particular structure, and you'll notice here that forming a pyramid. And this final chlorophyll molecule is very important. In your puzzle, we talked about P680 or P700. Well, that's what this molecule is right here. It's either P68 or P700, depending on whether or not we're talking about photosystem 1 or photosystem 2. So, light energy comes, or a photon of light comes, and hits these first chlorophyll molecules. And when the light hits it, electron in that metal, right here, in that metal atom gets excited, absorbs the photon, and bumps up to a new energy level. So that happens in each of these pigments here. But then that electron will fall back down and it will emit a photon of light. And if you can imagine, that's happening in both this and this chlorophyll molecule. And the next chlorophyll molecule actually absorbs both those photons of light. So the energy just doubles, it magnifies, and so on and so forth. Down each row, you'll notice there are fewer and fewer chlorophyll molecules each row. So by the time we get to this last pigment at the end right here, there's enough energy that's being emitted by these final two right here, such that we can take this electron from this metal atom, and instead of just bumping it up an energy level, we can actually, or the molecule actually kicks it off and creates what's called a high energy electron. So this high energy electron is special. It will be passed on to the ETS right here. So we're going to lose an electron from PS2, and it will go down this electron transport chain and do useful cellular work. It's then passed back on to photosystem 1, where the same thing happens. We have this cascade of energy coming down, exciting this electron again, so we get another HEE, high energy electron, which again will be passed down this ETS right here. And where does this electron come from? Well, you'll remember again from your puzzle that this process called the photolysis of water happens. So H2O is split into H plus ions and O2. The H plus ions are going to be important later on. We'll talk about that tomorrow. And O2 is just a byproduct, a waste product of photosynthesis. So this will diffuse out through the stomata. Another really important, well actually the integral piece of photolysis is that electrons are released to the photosystems in the splitting up of water. So that's the real purpose of the photolysis of water, is to donate electrons to these photosystems, because they're always passing them off down their ETSs. And they'll actually be taken away at the end of the ETS, and that is something for tomorrow's screencast. Okay, I think that is it for now. I'm going to upload this right away to YouTube. So, hope you enjoyed.